Welcome to a quick video that I'd like to show you some techniques we use on generating complex shapes and surfaces for vac forming. And like everything we do here at Custom Entertainment Solutions is starting with 3D CAD. And we do this especially when it gets to complex things. This surface is a very well designed, very tight surface to the technical specs we need to have it fit. Now from the CAD model it's also beneficial because we can use this in a number of different ways. Virtually you can go through and do things like analysis. Here's a computational fluid dynamics analysis, airflow blowing over this shape. Now does it really matter in this case? No, not for this application, but it's fun to see that, and that's actually how we use that model over and over again. In analysis we see little airflow recirculation patterns and whatnot, things like that. Now back to the model. We're using this model. It is essentially a pattern, or a lot of people call that a buck, for vac forming. That's our master pattern there. So from that pattern I want to make sure another analysis is done. I'm going to do a draft analysis, and we're going to see as we pull this plastic off, are we going to have any undercuts that are going to stop the show here. And sure enough, there's a couple of red areas on that design that are going to cause some issues. Okay, now you're right, they should not have any undercuts if you're making a vac form pattern, but we have a number of techniques we use here, and some specific ones to vac forming, that we've been able to pull very complex shapes that should not technically be able to be pulled from a vac form machine successfully. So we have ways of doing it, but in this case let's stay to the game plan here, just go forward with that. The next question we've got to ask ourselves is, how are we going to make this shape? And of course we're going to have to use a CNC milling process in here, because we're not going to go old school back to stations and internal stations, start sculpting that. No. We're going to use CNC. It's faster. It'll be more accurate. Now that leaves a whole other set of questions. Alright, so we know we're not going to use aluminum. We don't need to. We don't need tool steel here, okay? But we can go through styling foam. 5-pound urethane foam is what we like to use typically, and it could be wrench shape, could be a number of different things. And we also know we don't need a huge amount of accuracy in this final part. So if you look closely at the foam blocks, there's a bunch of what is truly auto body filler, which if you've ever worked with it, it's a great adhesive for sticking foam blocks together. You have to be very careful though when you're finishing that you pay attention to the difference in density. They'll finish totally different. So when you're doing your hand filing later on, it will show up if you're not very careful. Alright, so anyways, we can use that. That is great because we can rip through that fast. We can go high-speed machining on this stuff and be done quick. If we do this smart, now we could do a couple of things. We had a little undercut. Now if we get hung up on the details and we just pass that over the fence to a machinist, they would probably want to go through and do a fifth axis positioning on that. It's not necessary here, okay? This is not that kind of product. We need to be done with this fast. We don't want to spend 3 days waiting for a part to be done in a mill and spend who knows how much having somebody write the code for that one. We can go with a 3-axis live process. And what we're going to do here is that exactly, and you'll see that in these videos. We're doing a lot of X parallel cuts, some Y double overs, and then we're going to do some waterline cuts too that will take care of the small details. First off, we're going to rough this thing out with a 3/4 flat 2-flute high-speed end mill. And it is going to get rid of a lot of that volume that we just don't need. And I want to clear it away so that when I send my my double flute 1/4-inch ball end mill with a 3-inch long cutting length into that, it's not going to hit and clash with a bunch of material that should be gone. So that's where we're going, 3.5. It'll do it faster. We're not going to spend a day or two milling this thing. This thing should be done in about an hour at most. Okay, and we're doing this because we don't need super high accuracy out of this thing. Okay, scallopite is a thing that I want to cover real quick. Scallops are, if you're new to this world, let's imagine you take a ball end mill and you run it over a surface. There's one pass. You're holding your y-axis steady, but you're going in X, and you're traveling up and down in Z as it follows that surface. Alright, there's one pass. Now, the next pass you increment up in your Y, and it's a little bit over, right? And then it's going to do the same thing. It's going to track along in X, and it's going to follow up and down in Z. Now, you've got two passes, but between those, because of the ball end shape and the surface shape, you're going to have a slight piece of material that's coming out of the surface that technically should not be part of that surface. That's the scallop. Alright, as measured from the normal of the surface at any point, we call it the scallop height. Now, your scallop height can just cause you nightmares. If you're thinking about it, and it's your first time, go, I don't want any scallops. I want it to be exactly, as much as possible, like what my CAD model is, or my surface design was. Well, okay. So as you increase the scallop height, you decrease exponentially the time it takes to run the program. So keep that in mind. If I set my scallop height down to 5/10, a program that I could have run in an hour is going to take 3 days. It's not a linear relationship typically. So you got to watch out for that. Here's the deal. In this case, we're using styling foam. We're going to do a lot of hand finishing in the end. I'll show you that. And here's the thing is, we can actually knock this part out in an hour maybe and be done with that. We're going to have scallops. They may be 5 thou off of that surface, but you know, it's not a big deal. Consider in the end, this is a pattern that we're going to use for vac forming that does not have to be highly accurate. Alright, we're not making a mirrored surface here. It's going to get covered by a 1/16 inch thick of white polystyrene. Alright, so keep everything in mind. You could have just wasted days and many dollars going for what you think you need, and you really don't. We're going to get the same result. We're going to get it a lot faster though, and that's an important little point there. So watch out for your scallop heights and your strategy overall when you plan a 3-axis or really surface milling process. So we're done with this process. We got the buck out, and here's the urethane and Bondo part here that we're going to have to finish. The thing that you're going to see in this next shot is a little bit, it looks like it's dusted with black paint, and that's exactly what it is. If you've been exposed to this world of pattern making or autobody finishing, that's called a guide coat, and it's very simple. It's, in this case, it's just ultra flat black paint that just been lightly dusted over with just a rattle can, and that's going to show you where you hit with your file. And sandpaper, and a lot of people will say this, sandpaper is not called sandpaper when you're doing pattern work. Those are all called files. So I'm going to take my 220 grit file, okay, and I'm going to start working the surface very carefully. I can see exactly where I've touched it and what condition I've left it in as that guide coat gets removed. So your scallops should end up being the natural color of the foam, if that makes sense. That's going to help me guide and keep hold lines fairly consistent. And that's really why we just do that. So that's it. That's what we do. We put the guide coat on, we get it fairly close, and we just saved days by using a little bit of handwork there, and done. We don't need it to be absolutely perfect here. There's no GD&T here. They're not going to grade this class A surface with anything here. We're not doing that. We just need the pattern for the vac form. Okay, so air vents, another quick thing. I like to stay less than 1/16 inch diameter, depending on the thickness of the plastic that I'm using, of course. But what will happen is, many times people don't realize this, is you might have a form that in some parts may be only a 1/4 inch thick. So you drill a hole through that, that's fine. But other parts of the buck may be 3, 4, 5, 6 inches thick, who knows? And they use an aircraft drill and drill a 1/16 inch diameter hole through the same thing. Well, it's kind of common sense, but back to the computational fluids world that we also take care of in our designs. Fluid mechanics also applies to air, if you're new to this. Air pressure, the pressure drop from a 1/4 inch long hole to a 3 inch long hole, in your minds, I'm sure you guys can see this, is tremendously different. Okay, so as you're pulling that vacuum, you want everything simultaneous typically and uniform to be pulled down onto your pattern or your buck. It's not going to happen if you've got a 3 inch long hole compared to a 1/4 inch long hole. There's a couple ways around this though. I want to keep that hole diameter the same because I don't want to have a big indent in my pattern just because I'm trying to get more airflow. That's a little bit stupid. What I would do instead, and what we typically do, is network the holes together, and you'll see that on the bottom of this pattern. And that looks like a mole has crawled through the bottom of the pattern through each hole, and that's really what it's going through and doing, is it connects all those passages, those airways, so that you, for one, even if one gets blocked by whatever's on your vac table, it will pick up a passage and be able to still have airflow through it. Now, the other side of this too is you can actually go through and hog out material so that you get to that point where that hole that was filled with 3 inches of material, now you can actually shave that down and hog out the material so it's not 3 inches, maybe it's an inch or less or something like that. So that can help out the whole process here too. I think you'll find that people have been doing vac forming a lot, and unique vac forming, not factory line blister packaging. We're making 10,000 things a day. When you run into a unique pattern that you haven't pulled a form on, haven't pulled any plastic on yet, you're going to get surprised every now and again. And you'll learn these tips and tricks and be able to see where you're going to have problems, where not. We've pulled this exactly right how we wanted to the first time, and it's just because we've been doing it for years. But here's another couple tips that will help you out. So the air vents, we network them. The final vacuum on our system here, the first thing we do is we actually set the pattern of the buck on the table, and you'll see there's multiple vents in our table system, and some go with a single port. I don't like that so much, because if you lose a plastic edge in your frame, say your plastic starts shrinking away, well, your whole plastic sheet right there is shot. You got to chuck it. Now, if you have multiple ports and you have cotton gloves and you're doing your right job, you can pull that down. If it starts to pull away, you can push that down with your hand. All the other ports on the table that you see there will cover the rest of the business there for the most part, and keep your airtight seal, so you can save your material and keep a good part. Now, the other side of this too is we start our initial vacuum with just a 5 horsepower vacuum, okay, and that's what we use to set essentially the plastic in place. If you see on the video, you'll hear a secondary psh, and that's because we use a real high vacuum. It's a Welch pump that pulls air out of a reservoir tank, and we pull it out to about -20 inches of mercury, which at our altitude is about 6 inches of mercury above what would be an absolute zero pressure. This high vacuum, second stage, makes a huge difference, and you can see it on the video, but especially when you're trying to do more detailed work with a vac form, yeah, that'll pull out details that will be absolutely missed if you don't have that. So what seems like an unnecessary step in the machine is actually very critical. So that's how we get this last part. We're happy with it. It's drafted on the sides, so we can pop that right out. Another tip is we usually, if we have a hard time, we'll take a little bit of an air nozzle and just pop it out through one of the vents, and it's done. Next form, please. So anyways, tips on the speed from the CAD. We go into analysis, draft analysis. We had a little bit of fun with CFD analysis too. See the airflow over that thing. But then especially going to surface milling, some of the tips and tricks that we use here just to get it done fast. If we can do that, if we need more accuracy, we'll do that too. It's just going to take a little bit more time. And then finally doing the guide coat finishing, and then the final buck design is critical. And I wanted to share that with you guys, and that's how we do it over here. As fast as possible, or as fast as we can push it, and still get exactly the quality that we want out of that. If anybody has any questions, please feel free to comment on this. Love the comments, and you know where to find us, www.customentsolutions.com. Cheers.